host. Yeah.
Exactly. And we're recording. Great. And people are starting to come in. Hi, everyone. I see the number trickling up, so we'll just give everyone a few moments to come on in and get situated before we really get started. Let's give everyone a few moments. Hope everyone's having a nice beginning to their year. This is the first meetup we have of 2021. So it's, good auspicious start. I'll wait a few moments before I do the announcements just to make sure we get as many people in here as possible, so everyone could hear everything. We have a lot of good stuff. So I love watching the number tick up slowly but surely. All right, seems to be there's a bit of an inflection point in the numbers. All right, so I'll slowly get started doing it. We already have a first question. If I could find the chat window, oh, that's nice. It works a little better now. Pele's asking, saying thank you first, and then saying will it be available. Yes, the talk will be available. In fact, all the talks are available at nyhackr.org. There's a presentations page where we have both the slides and we have the video available. In fact, there's about 11 years worth of slides up on that site. And no, 12, almost 11 and a half years, let's call it 11 and a half years of slides, and about 6 to 7 years of videos. So there's actually a really great resource, really great. I see, Pele, you're new to the group. I'm glad you're here. It's the NYHackR is really a really great resource for finding knowledge, like literally going back 11 years worth of slides. So we have a lot of stuff up there. So the very first thing, those of you that have been coming in person, the first thing I like to always do at the meetup is say who is hiring. Of course, that is difficult when we are in this Zoom format. So what we're going to do is, in the Slack channel, for those of you who haven't joined, you can go to nyhackr.org/slack.html, and you can join the NYHackR Slack. There is a channel, job postings. You can go there and post any job you'd like to hire people for. Being that I am on screen and I am organizing, I'm going to cheat a little bit and say, hey, I'm hiring. I am looking to hire 2 positions, an account executive to help us service our customers, and an events and marketing coordinator. And the really cool thing about the events and marketing coordinator, not only do you get to help out Lander Analytics market ourselves, you get to work on the R conferences. Right now it's the New York R conference, the R government conference with planned expansions when the pandemic ends. You get to work on that with me. So if you want to come work at my company, either doing sales or doing events and marketing, go to landeranalytics.com/careers, and you can find both job postings. So come on, we'll be hiring shortly. So if you want to apply now. For today's talk, but in general, we have this Slack team. I guess they're called Slack teams. And we have lots of different channels up there. We have R help, we have Python help, Git help, there's Stan help, there's a COVID-19 channel, there's an events channel for any events in the community, whether it's a meetup, a conference, or things outside the community that are cool events. There's a channel for that. All sorts of different channels for being involved in the community. Specifically for tonight, there is a channel called Jan 27 Meetup. This used to be December 1 meetup. Before that was November something meetup. We just keep the same one going because it's easier than making everyone rejoin the channel. So go in there. If you want to chat with each other about what's going on in the talk tonight, jump in there. And I say tonight, I understand we have people coming from different parts of the world. In this 24-hour block of time, that's what you're going to be looking for in there. So find that channel and go in there. Since we can't have questions like we normally would in person, as I think we're all aware by now of Zoom, please ask your questions either in the chat here in Zoom or in that Slack channel. Again, the Slack channel is Jan 27 Meetup. You ask the questions there, I will collate the questions, and at the end or in the middle, if there's like a nice break point, I will ask Daniel the question and he will answer them. Unless he refuses to answer. I don't see why he would, but you never know. But so please go into Slack and ask your channels or into the chat right here. I will collate them and make sure they all get asked and seen. Speaking of the conferences that I mentioned when I mentioned my job posting, last month we had the R in Government conference. It used to be the DCR conference, but now it's R in Government. The videos are just being finished now. It takes a while to get the videos up. We have lots of speakers. We have really high quality editing. actually a videographer and producer, used to be a producer for NFL Films, and perhaps more importantly for Double Dare on Nickelodeon. So we put a lot of really great care into our videos. He's just finishing them up now. In fact, the only thing holding them up is me reviewing them. I'm going to get them reviewed and they'll be posted at rstats.ai. Up there, you'll see actually we have 6 years worth of conference videos. It's a really great resource. So I hope everyone has a chance to look at them, and we will be sending out an email to the whole group as soon as we get those videos posted up on rstats.ai. That will go faster as soon as we get the events person in place. Hint, hint. I want to thank EcoHealth Alliance for providing the Zoom. They've been providing the Zoom since April when we started doing this virtually, which I think is really fitting because they researched coronaviruses amongst many other things. So it's nice they've been doing this. So thank you, Noam and Emma, for helping us out all these months. It's been a great help, you providing this platform for us to reach all of the audience. It's really made a big difference in letting us continue on with our, I want to say our mission, but these fun things we do to help spread the knowledge of R. Of course, you all know this, there is no bar afterwards because, you know, we're in video land. What we did back, I think in October, November, we had a special meetup with no speaker, just hanging out and, you know, socializing. I didn't want to say drinking because like some people drink alcohol, some people drink soda and water, some people have pizza, some people had snacks. Maybe we'll do that again next month. In addition to the meetup, we'll do a hangout just so people can, you know, get to see each other. That's one of the things we love about this meetup is everyone hanging out with each other afterwards and getting to know each other. So maybe we'll plan one of those. I know it was really popular. We'll aim to do that next month. Likewise, we can't do our normal pizza poll because we don't all have the same pizza. In fact, my pizza isn't even here yet. Normally I have to show off the pizza, but here's an empty void of my pizza. It's coming. I don't know when it is, so I can't show you the cheese lock. I can't show you the underside for how it's charred, but it will be coming. I think I got a Brooklyn pie again. I'm really into those lately. Maybe it's a round pie. My wife Becky ordered it, so we'll see, you know, what she ordered when it gets here. I hope everyone is enjoying whatever you're eating. Hopefully pizza, but if it's another food, I hope you're enjoying that. That's a big part of this meetup community. You know how much I love involving food. So I think that's everything we have to go over. Remember, jobs, you want to post a job, do it in the job postings channel. You want to apply for a job at my company, go to landeranalytics.com. If you have questions, go to the Jan 27 meetup. The videos will be posted at nyhackguard.org. The videos for the conference will be at rstats.ai. And I believe that is everything. I see a bunch of people saying hi in the meetup channel. That's great. I hope everyone there gets to have a good time. So Lauren's saying we should do a double blind pizza orderings and tastings. Normally we do a not blind at all pizza ratings. In fact, if you were to go to bit.ly/pizza poll, all lowercase, you will see like 8 years worth of pizza poll data. We've been collecting this for 8 years, so much so that Thomas Levine even made a painting of bar charts of the pizza data that we had put up for auction at the conference, and the Robinson siblings were very gracious. They wanted an auction and gave it to me. So it's hanging in my office, which I haven't been to in a year. And I love that painting. So we do collect data. We love this data. With that, I am very excited. You know, for years, you could do neural networks in R for decades, thanks to Brian Ripley's. Sorry, I had to drop. Yeah, someone said I should have made a pie chart instead of a bar chart. Actually, it's funny you say that. Tidy Tuesday, that community, they used the pizza data for one of their Tidy Tuesdays challenge, and people did a lot of faceted pie charts. So it's up there somewhere in Tidy Tuesday. People did the pie chart exactly that. So there you go. So even though I'll do neural networks in R, thanks to Brian Ripley for decades using the NNet package. But deep learning is a different beast. A few years ago, the good folks at RStudio came out with Keras and TensorFlow, which open up modern deep learning into R, but you had to go through Python. So I've been really excited to watch this come through of Torch, which goes straight to libs to is either C or C++. I'll let our speaker tell us that. I've been really excited for this because I don't have to manage a Python installation for these projects. Nothing wrong with Python, but I want one language at a time to make my personal life a little bit easier. So I'm super excited for this. I've been chasing Daniel for a few months to get him to speak. I'm super glad he's here. Everyone, please give a virtual warm applause to Daniel, who's going to guide us through the Torch package, which seems really, really awesome. I have my own personal anecdotes about how cool it is. I did a 50,000 row distance matrix in 0.03 seconds on a GPU of Torch. So thank you, Daniel, personally. Everyone, welcome Daniel to come give a talk here.
Thanks very much, Jared. Thanks for inviting, and I'm happy to be here, and thanks everyone that is watching. I'm going to share my screen now, so just a second. And I think everyone can see my screen now. So I'm going to talk about, just as a disclaimer before starting, like I'm not a native English speaker, so sorry for my English, and I hope you can understand everything I am saying, and feel free to ask questions during the talk. So I'm going to talk about the torch for our project today. And my name is Daniel. I live in São Paulo, Brazil, and I'm a software engineer at our studio. And I work in the multiverse team. We are a group of 3 at the moment, and we work on Torch, TensorFlow, and Sparkly ARM mostly. Today I'm going to talk about what is Torch and a little bit of the Torch components and how they are tied to each other. And then I'll talk how you can help us with Torch and how to contribute. And next, some of our future work or something that we are planning to work on in 2021. So what is Torch? Torch is just an R package with 2 core features. It has an array computation library with strong GPU acceleration. So you can everything that you can do in Torch on your CPU, you can mostly do on a GPU and benefit of like 10 times speed improvements usually. And it also has a deep neural networks library built on this AutoGrad system that I'll talk in a few minutes. So why Torch? Torch for R is based on PyTorch, and PyTorch, if I don't know if everyone is familiar to PyTorch. So PyTorch is a framework for deep learning that has very rapidly grown in popularity among especially researchers. And I'm not saying that like still TensorFlow is probably the larger framework for deep learning, but like if you see papers on arXiv, which is what this plot is showing, like you see that PyTorch has grown a lot in implementations of models. And so we believe that Torch can help the R community to accelerate machine learning algorithms because it has a very convenient interface to implement all this array computation. So I know that many of you might compare Torch with TensorFlow for R, and I will avoid this question because I work on both projects, and I think both are super great projects. So here I'll just say like some facts that I think is good to know before. So Torch is mostly in early development. So we released the first version of Torch 3 or 4 months ago, while TensorFlow is much more mature in R. It has like, I think the first release was in 2017. So it has almost 4 years now. Torch uses libtorch, which is the C++ library behind PyTorch, while TensorFlow uses the Python implementation via reticulate. So this is a big difference. And Torch in general has a more lower level API than Keras, for example. So if you are used to Keras, you'll see that Torch is more verbose and more lower level in a sense. So this is also important to know. I'll just like talk about the Torch for our implementation. So deep down, there is libtorch, which is this C++ library that powers PyTorch. So all the logic for Torch, for tensors, for the autograd is implemented in libtorch. And there could be like a Python box here. So Python is tied directly to libtorch. And here's the architecture for the torch for our project. So libtorch is a C++ library, and especially on Windows, it's only compilable with a specific compiler called Visual Studio. And this compiler doesn't talk very well with R. So we have implemented, and I mean, it was mostly Javier Luraski at our studio that implemented this lantern layer, which we called lantern, which is basically a C API to libtorch. So we can tie together libtorch with R, especially on Windows. And then we have auto-generated RCPP wrappers that talks to this C API. And then next we have this torch, all this torch underscore something functions. And both these layers are auto-generated code from, like, it's basically an R script that generates code that wraps all the C functionality. And on top of that, we have implemented in R all some neural network models, optimizers, and data sets logics. So one thing that I think it's cool of Torch is that all this is implemented in R, and you can easily look at the code and see what does this optimizer is doing, or what is this neural network model doing. So I'll talk more about all this in a few minutes. So just to motivate Torch, and I think like the lower level stuff in Torch, I want to give an example of something that Torch is good to, and it's mostly hard to do in R if you something a little bit more complicated than that. So this is like the lowest, the minimal example of something practical that you can do with Torch. So here I have this, I'll simply load Torch and ggplot, and then I have this function f here that just takes an input x and squares it and does minus x. So this is a parabola like that. Let's see if I can show you. Yeah, it's simply a parabola here. And think that you want to use some algorithm to find the minimum value of this function. So imagine that you want to find the minimum, the y-axis, and for that you want to use some kind of gradient descent algorithm. So one thing that to implement the gradient descent algorithm in R, in base R, or mostly like that, you would need to know how to compute the derivatives of this function. And like, I don't know if you have ever done some math class in the university, and I think this is probably one of the first things that you learn in a math class in the university, is how to compute the derivative of a function. And we can just say that the derivative of f relative to x here is this other function here, okay? So, and now, like if I am implementing gradient descent, I'm going to start with an x value that it's -2. So I start here in this curve, and I want to an iterative algorithm that will go down through this parabola and end up in the minimum value here. So this learning rate I'll not comment now, and neither these segments table here, because it's just like for practical examples. And so I start my x value, and then I run this for loop. And what I'm doing here is like, I just save the starting value, and then I update x in the direction of the derivative of f related to x here, and multiply it by this learning rate. If this learning rate value is too large, I'm saying like I believe very much in this gradient for a sample, and I really want to go in that direction. But usually we don't believe too much in these estimates, because we are doing this with samples and everything. So we usually use a small learning rate for that. But anyways, and then we can see like the steps of this algorithm like this. And so we started at x -2, which was giving us -6 in the y-axis. And then we went down to here, and then the next step of the algorithm, when we went down one more step and one more step, and then we ended up in the minimum of this function, right? So each arrow here is showing like the starting point and the end point here of this, and the end of each iteration of the algorithm. And we see that in the end we found x equals 0.4. That is approximate the minimum of this function. Okay, and you might be wondering what does that relate to torch, and we will get to that in the slides in a few minutes. So I'm going back to torch now. Okay, so torch has these components, and so torch is mostly split in these components. It has tensors, and tensors is really the main data structure in torch. Everything in torch works with tensors, and tensors are like the data here, or the parameters, or everything that that fits in this data structure. Or tensors are like arrays in our general arrays. Okay. Then Torch has the array computation library, which works with tensors. So all these functions in this array computation library takes tensors and do something with them, like creating some, like taking the mean of a tensor, or doing a convolution in a tensor, or anything that you want. The other component of Torch is AutoGrad, and we will talk about that later, but AutoGrad is responsible for computing derivatives or gradients in an automated way. Then we have and then we have the higher level models in Torch. So we have the NN models, which I'm going to, and we have the just-in-time compiler that I'll also talk about. So these are the main torch components at the moment. So let's start with tensors. Tensors are like a continuous array of memory, like a pointer to an array of memory in your computer. And tensors have a few attributes that are important. So they have a data type. So a tensor can be an integer tensor or a float tensor, a double tensor, or anything that you want. Tensors can have a device, and the device in Torch4R is like you want your tensor to be on the GPU or on the CPU, or like if you have 3 GPUs, and in what GPU do you want to place this tensor? So this is the device of a tensor. A tensor like is a continuous array of memory, so it also has an attribute like its dimensions. So a tensor can have like any dimension that you want, and tensor has the tensor object in R has also has a lot of methods, and I'll talk about that later. And another important attribute is required grad of a tensor. And this is related to autograd, and I'll make it more clear when I talk about autograd. Tensors also have a layout, but like it starts to become too much. I'm not going to talk about layouts of tensors. So tensors can be created from R objects, and for that you use the torch tensor function. So you just call torch tensor in an R object, in an atomic R object, and you get a torch tensor. So currently we only support integer and doubles and logicals. So you can't convert R character vectors or R complex vectors to torch tensors, but this can be implemented in the future. So yeah, you get, if you convert an integer tensor, you got a long tensor in torch. If you convert a numeric matrix from R, you get a float tensor in torch, okay? So this is like a design decision that might be important for some of you. So basically numeric values in R are doubles, but when we convert from R to torch, we usually convert to float because this is what's mostly the mostly used data type in deep learning because it's faster than computing stuff in double precision. So you will get a float if you convert an R vector and an R numeric vector to a tensor. And then, like, if you, this is how you convert R objects to tensors, but you can also create torch tensors directly from torch. And we have many initialization functions, like for example, torch rand n. This will initialize random numbers with normal distribution. And what you put in the parameters is the dimensions of the tensor that you want to create. So here I'm creating a 2x2 matrix with standard normal distribution. And if I put a single number, I'm creating a length 3 vector, and rand, instead of rand n, creates an uniform using an uniform distribution. And we have many other functions like that. Tensors also support indexing, and one important difference from R indexing is that negative indexing doesn't like remove elements from the object, and it's more like in Python, it will take elements from the end of the tensor, okay? So suppose you have torch tensor 1 to 5 here. If you index with 1, you will get the first element. And if you do x minus 1, you get the last element of this tensor. So I considered using like mine to use the same logic as R, but I think this is more useful. Like usually it's hard to find the last 10 elements in R or something. You have to write a bunch of things inside the indexing. So this helps a little bit for some stuff. And there's a whole article about indexing in this link. So you can also do interval selection with indexing, and there's one. There are a few of these synthetic sugar for tensors. Like if you have a tensor with 3 dimensions and you just want to index in the last dimension, for example, you can use a dot inside the indexing operator here, and this means like take all dimensions before this one. So it doesn't matter if the tensor has 2 or 3 or 4 dimensions, it will always use the last dimension here. And you can also use, by default, we drop dimensions when you select a single dimension, but you can, just like in our add drop equals false to avoid dropping that dimension. And you can also like add a new dimension to the end with this syntax sugar new axis. So this means like, please add a new axis in the end of this tensor. So this is just like some nice features, I guess. And you can also subset assign tensors, and that's all about indexing, right? And then we use the dollar operator to access attributes of tensors. So you can find the shape of a tensor with dollar shape. You can find its data type. So x dollar d type gives us the data type. And if you do x dollar device, you get the device, and x dollar requires grad gives this attribute. Okay, so this is how you access attributes of tensors. And you use the to function to modify attributes of a tensor too. So suppose I have an integer tensor here that is like a long tensor in R, and then we want to convert it, to cast it to a float tensor. You can do x2 the type equals float, torch float, and then you get a float tensor. And if you want to change the device, you can also do x dollar to device, and then this tensor is copied to the CPU device, for example. And this is the, like, I think most of what I have about tensors. And then we have the array computation library. So Torch has around 200 functions and methods to manipulate tensors. Torch is, PyTorch is mostly inspired by NumPy. So everything that you can do in Torch, in PyTorch, is mostly one-to-one with NumPy. And we have the same functionality here. So you can take the mean of a tensor, you can sum tensors, you can do convolutions, and many other things like take the median and all that. And one thing that is nice is that if your tensor is in the CPU, it will use the CPU backend for the computation. If your tensor is in the GPU, it will use the GPU backend, and it will automatically use the GPU acceleration. And there's one thing that is important to note is that there's some duplicated functionality. Like there's a lot of stuff that you can do with torch functions and also do with methods of tensors. So for example, these are equivalent operations, like torch min of x is equivalent to do x dollar min and call this method, right? And yeah, you can see the full list of functions in this link. I won't like open now. Like there are a few like I find useful and maybe hard to find if ever I need to use this. So if you need to combine like doing dplyr bind rows with tensors, you use this torch cat function, and this will like pile up to tensors, and you can also split tensors with the unbind function. So this might be useful somewhere, I don't know. Yeah, so methods are accessed with the dollar operator, just like the attributes of tensors, and you call x dollar min to get the mean of a tensor. And one thing that is important to note is that x dollar add with an underscore in the end is something that works in place. So if you do every method that ends with an underscore is an in-place operation. So that means that if you do this, and note here that I'm saving this to an y variable here, but when I call x again, it's modified. So this modifies x in place, and there are some cases that it will be useful to modify stuff in place, right? And now I'll talk about autograd. So what is autograd? Autograd is like I don't know, a model in Torch that can automatically compute exact derivative of tensor operations. So any operation that you can do with Torch is trackable by this autograd system. And this means that you can compute the derivative of that transformation after you did this, after you did it. And this is the main feature that allows us to use Torch for deep learning, because in deep learning, we are always doing gradient descent or some kind of gradient descent. And you will eventually need to compute derivatives of complex operations. And then you will need an autograd system for that. Otherwise, you won't be able to finish your work in time, because you will be calculating derivatives by hand, and it takes too long. So here is an example of autograd in action. So suppose I have this x tensor here that has the 2 as a value, and I mark it with this required grad equals true attribute. And now I do this computation with it. It's like x po 3, and I get a value here, like I'll get 8 here, okay? And now I call x dollar backward. And what this function does is like, it will go over all operations that it will go over all tensors that were used to compute y at that have this require grad equals true attribute, and populate this grad attribute. And this grad attribute is like the derivative of y over x. So we have this value here. So x grad is 12, because if you do the derivative of x po 3, you have 3 times x po 2, right? So this is the idea here. So AutoGrad, I mean, it's John Carmack that is saying this here, but I mean, AutoGrad is nice because you don't have to implement all the derivative logic just to test an idea, and it simply just works when uh, you do your computation, and then you just get the derivatives, and that's all. You don't have any more work for getting it. So it's a nice feature. And now what I like to show you is like how we can write this example that we hard coded the derivative here, and we updated the weight and everything using Torch. So first of all, we have like the same parabola that we want to find the minimum here, right? And now what uh, I left this here, but we won't use this function now. So basically what we have here is like, I'll define this torch tensor with the -2 value, and I'll mark it with the requires grad equals true flag. And then I have this tensor. This works just like any normal tensor that requires grad, doesn't change anything for the computation and like that. And now I do y equals f of x. And I have y equals 6 because it's 2 times x minus, it's x power 2 minus x. So this gives us 6. And then I do this y backward here. And this doesn't return anything, but it modifies the x grad attribute. And when we do this, we got -5. And this is exactly what the value of df dx would be, right? So notice that I didn't need to implement this function by hand or hard code it, because Torch can compute the derivative, this derivative automatically. Okay. And now we implement the gradient descent algorithm here, and we have like mostly the same stuff that we had in R, but with a few differences. So first of all, we need to zero the gradients, because every time you call y dollar backward, it will sum with the gradient that was already there. So if grad is -5 at the moment, and I call y backward again, then grad will be -10. And if I call y dollar backward again, it will be -15, and it goes like that. So we don't want, we usually don't want that. So we zero the gradients, and remember that methods that end up with an underscore modify the tensor in place. So this is important here. So x is now 0, x grad is now 0, right? And then we can like call y and backward again, and this is like the same thing that we were doing here, like x minus learning rate times df dx, but we use the in-place operations in Torch for that. So first we create a context that disables gradients, because we don't want this operation to be tracked by any AutoGrad system here. And then we do like subtract learning rate times the x gradient. Okay, and this gives us the same plot, because we are doing these steps here to go find the minimum of this function. Okay, so I can see like this code seems more complicated than the R code at the moment, but imagine that this function could be something much more complicated than that. Like, and like, if you add a simple convolution here, then it almost becomes intractable to calculate this, because this grows absurdly. And there's no easy way to compute the derivatives for that. So this is the minimal example of what AutoGrad does, but of course, like, if you know how to compute the derivatives by hand, and it's just one single line of code, then it's fine. Okay, and another thing about AutoGrad is that it supports extensions, and you can, for example, suppose you have a function that is not composable of any of the torch computations that you can do. And or, for example, you have a function that you can really speed up its derivative computation if you knew that the operations would be in a specific order. For example, you can implement a new AutoGrad function, and when you do this, you implement a forward method and a backward method, and this is like you implement the function and the FDX, for example. So this would be something like that, and then you can use this function with as it were any other tensor operation in Torch, and with AutoGrad and all that. There's specific docs for that. I like to highlight this feature because this is something that is only allowed because we have a deep integration with this libtorch library, C++ library. Otherwise, it would be almost impossible to do this kind of stuff directly in R. And if you want to learn more about AutoGrad, you should definitely read Sigrid, my colleague at RStudio, the Introducing AutoGrad blog post in the RStudio AI blog. And if you are interested in the details of the implementation of AutoGrad, you should go to the white paper of the PyTorch team, explaining how they implemented that in PyTorch. Okay, so now I'll go through the higher level abstractions in Torch, and the first one is the neural network models. So in Torch, all models and layers, if you have ever used Keras, so both models and layers are what we call NN models. And a model is like, think of models and layers like they are just functions that take that transform input data, but they have these parameters or these weights that are like the state of this function. So this is the abstraction we are going to use for models. So think about a model as a function. It's basically a function that takes input data, but this function has a state that you want to keep updating. So every step in the gradient descent, for example, you update the state of the model. And the NN model in Torch makes it easy to handle these functions and the state of these functions. So in R, one way you could have functions with state is like creating a function factory that returns a function, and like since this function is created in this environment, it will know, like, it will find W and B here because they are in this enclosing environment, right? So this would be one way to implement an N mod, a model in R, in pure R, without any like other abstractions. But then it's hard to access this environment and finding W and B or any other states that you have here. So like when we use an N model, we do it in a slightly different way. So to create an NN model, we use this NN model function, and we pass two methods to it. You need to implement the initialize method and the forward method. So the initialize method is where you will create and define mostly all the state of your function. So this keeps things really separated. So in initialize, you implement the state of your function, and in the forward method, you implement what your function does with that state and an input tensor or an input data. So this gives a when you this NN model function call gives you mostly like a generator that you can use to initialize layers. So this, for example, is the implementation of a simple linear model in Torch, where you like define the W weights, the weight and the bias, like, and they are initialized here. And the forward is just like the matrix multiplication between input and the weights and adding the bias. And yeah, sorry. And here we have the exact same thing as in R. So this acts just like a function, and then you can call it in an input tensor. But NN models in Torch makes it very easy to handle this state. So for example, if you do linear dollar parameters, it will give you a list of all parameters in that model. And if, for example, you want to access any specific parameter in the model, you can do linear dollar $W and you will find this parameter. And comparatively, it would be hard to do this if you use it base R, because you will need to find the environment of that function and list all tensors here, and what tensors there are parameters, or I don't know, like it would be hard to do this in R. And another thing that is useful for you that you get for free when using NN models is that you can move all the parameters of a model, for example, to the GPU. So if you do model $2 device equals CUDA here, for example, you move all the tensors that are here to the GPU. So this makes it easier to handle the state and move between devices, change the parameter, the data type of these parameters, and all that if you want. And yeah, one nice thing that is that all layers that exist in Torch, and we don't have all the layers that also exist in PyTorch yet, but it's like, I would say like 50% then. So all the implementations of the layers in R are directly implemented in R code. So it's not C++ code or Python code. So the nice thing is that you can easily like investigate what it's really doing, and And also you can like read the code and make it like and use it as an example to implement other models that you might be interested in. So this, for example, is the code implementing the linear model in Torch, and it fits in a screen. Like it's not like code from other planet. It's like it, I'm sure everyone can understand this code without knowing details about Torch, right? And yeah, models can also handle submodels. So if you have like a few submodels in a model, then like things become nicer because you can implement, you can reuse stuff. So for example, here this is the implementation of a multi-layer perceptron in Torch. And it has like a linear layer and then a relu and another linear layer. And I just call them in that order here. And if you call like MLP dollar parameters here, you'll see all the parameters that are living in this model, and not only the parameters that are implemented in how do I say this? Like you will see all parameters, including those of the submodels. So this is a good way. We will get to that, but it's how you handle the state of an NN model. There are also sequential models, which are basically like you just implement the list, you just pass the list of layers that you want. And since it's a sequential model, it will know that the forward method here would call everything in the order that you declared. So this become like less variables if you want. And for every NN, so every function in Torch that starts with NN underscore is like an NN model. But there are also functions that start with NNF underscore. And this is the functional API of Torch. And this is basically like lower level than this. And if you use the functional API, you are basically saying like, I don't need Torch to manage state. I'll manage state of these models somewhere else. I just want to call the same operation that it's doing, like the same forward operation. So this is how it's implemented in Torch. Like I just like you are mainly going to use NN underscore functions when you use Torch, but it's good to know because you always see NNF functions there if you use some kind of autocomplete or something like that. And we have almost complete feature parity with PyTorch on NNF underscore functions, but not on NN underscore layers or models. And then in Torch we have optimizers, and optimizers are Torch's abstraction for defining optimization steps. And the idea of an optimizer is to encapsulate all the code that is responsible for updating weights or parameters in models. And optimizers are also implemented in pure R code using Torch functions. And you can like see exactly how it is implemented without like needing to go to C++ code. And you can also implement new optimizers without knowing C++ and things like that. You can follow an implementation that already exists and modify stuff that you find that might be better for your problem. And yeah, like the implementation of stochastic gradient descent is, or gradient descent is more or less something like that. Like I showed in an example before. So for each parameter, you will subtract the gradient times learning rate. But it gets tricky when an optimizer has state, like add-in or SGD with momentum and stuff like that. So it's good to have an abstraction for that. And Torch has these optim functions, optim underscore functions, that takes a list of parameters and other parameters that the optimizer might have. For example, the SGD optimizer has the learning rate parameter. And then, like in your model, you just need to call optim zero grad and optim step, and this will automatically, like using the SGD algorithm, update all parameters that are in this list. So this makes it much easier to handle. Like if your model has many parameters, you just do a single call to optim $step, and then everything is done. Every parameter is updated. For SGD, you can find in the code, it will be like something like that, like a for loop for each parameter doing stuff like that. But other optimizers might have other ways to update the parameters that are a little bit different from that. And thanks to Krzysztof Joachimiak, we have, like, I think at the first release of Torch, we had only SGD and Adam because they are like the mostly used. But Krzysztof implemented like all these optimizers in Torch. So thanks to him, you can choose in a large list of optimizers here. And there's an issue for that. There are other optimizers, and if you want to contribute one, you can go to this link and find the list there and those that are missing. There are also learning rate schedulers, but I won't talk about that now. But if you want to learn about learning rate schedulers, you might want to read this blog post by Sigrid that is linked here, and she uses learning rate schedulers to optimize training. Next, we have data sets, and I think this might be the most complicated abstraction in Torch because it's very different for what we are used to in R. But I think it's important to know that. But one thing that I would say is, like, all this is optional in Torch. Like you can implement everything like that if you prefer. You don't need to use optimizers. You don't need to use models if you don't want to. You can implement your layers in a different way if you want. You don't need to use AutoGrad if you want to implement the derivatives by hand. You can also do that. And you don't need to use data sets too, but I think using data sets is nice because it provides some helpers for you to train your models without needing to figure out how to make it work, how to load data correctly and stuff like that, how to shuffle data, how to anyway. So if your data set, the Torch abstractions, the Torch data set abstraction is mainly focused on when your data set doesn't fit on RAN on your machine, on the RAN available in your machine. So basically, like, deep learning models don't need your data to be on RAN, all your data to be on RAN at the same time. You just need a batch of them, because we use a mini batch updates usually. So you just need to have a batch on memory, and the torch dataset helps with that. So when you implement a dataset in torch, you will use the dataset function, and then you implement the initialize method, the .getItem method, and the .length method. In the initialize function, you can do whatever you want here, but usually, like, it's a common pattern to download data or to get parameters to find the data on your computer or stuff like that. So for example, here I'm passing like paths to images, which would be a character vector in R with a bunch of paths, and the labels for each one of these paths. And then I save both of these values in the self object here. And the self object can be accessed by any of these other methods that you implement here. And so the .getItem method will take an index parameter, or I here, and will return this observation, this specific observation. So for example, here, like, if I index by this index here, we will in the .getItem method will read that image in this path and return a list of the image and its label that it was saved in this object labels here. So each time I call .getItem, I'll get a different image, but notice that I don't need to have all images loaded on RAN, because .getItem will read each image as it needs it, right? And then we have the .length method that just says like how to compute the size of this data set, or how many observations did this data set have. And yeah, that's it. We initialize a data set by passing the character vector of paths and their labels. And then, like, this object can be indexed, or you can also take the length of this object if you want. So if you index by 1, it will basically call .getItem with 1 here. If you do ds subset 2, it will basically call the .getItem with 2 here. So that's all. So dataset initialize can do anything that you want. You can prepare data, you can like compute intermediate files, you can like do anything that you want, download data, anything. And the .getItem function can also do anything that you want. So for image problems, it's common to use .getItem to read images from disk, but you could like query stuff from a database or from an REST API, I don't know. You could like do some kind of pre-processing there, or like do some kind of data augmentation, like in images, it's common to rotate images, or like do some kind of reverse mirroring transformation or stuff like that. And yeah, that's it. And since all data sets are basically pure R code too, you can find a bunch of examples of data sets that we already implemented and find like, how do I do that? And you can just look at R code and see how it works. And now there is the data loader, and data loaders are like are function. Data loaders is another abstraction, and data loaders takes data sets, and they can iterate over this data set, and they can take. And the main idea of a data loader is to take batches of a data set. So usually in deep learning, I mean, the in deep learning you usually use mini batch algorithms. So you need to load a batch of data, and the dataset abstraction is tailored to read one observation with the .getItem method, and data loaders will basically read like a batch or call .getItem for multiple indexes. And data loaders can shuffle things, and they are an easy abstractions, and they are like they try to solve this problem of iterating over data sets, right? And you use this enumerate function, like, and this will load one batch at a time, and this can shuffle stuff and all that. Another thing that is useful of data loaders is that they can load batches in parallel. So suppose you have you are reading an image from disk, and I mean this is a costly operation, and sometimes this is the bottleneck of your model, like loading the data to run through the model. And but you can like have parallel R sessions loading data, and your model processing them sequentially, but the data is loaded in parallel. So if you add this non-worker argument to data loaders, you can basically like read batches of data in parallel, so it should be much faster. And it's not always faster, because there are a few things that you might need to consider. So this is a benchmark. I think I won't comment that at this time, but like there are mainly three things that you need to, before using parallel data loaders, you need to think about the number of workers that you can have. This is usually related to how many cores your machine has, or something like that. Then you need to think about the time that it takes to run .getItem. So if .getItem is very, very fast, then there's no sense to use parallel data loaders, because the overhead of using parallel stuff won't compensate the time that you will gain by doing stuff in parallel. And another thing to consider is the size of the returned tensor. So if the tensor you are loading in memory is very, very big, then it might not be adequate to use parallel data loaders, because basically batches are loaded in different R sessions, and you need to pass data over these sessions. And passing data between sessions is a costly operation, and it doesn't, if your tensors are too big, then it won't compensate doing stuff in parallel. So it's a trade-off of these three things that you need to consider when using parallel data loaders. But I mean, maybe the easiest way to find out is like running the model the first time with many workers and see if it's faster than sequentially, and that's all. Like just benchmark and see if it's faster. If it's not faster, just use sequential. That's all. And then I was going to do a full example, but I think I'm really out of time. Like I spent a lot of time talking, so I'll skip that one and like leave it for you. But I want to talk about some other things. So one thing that I talked about in the beginning is the JIT, the just-in-time compiler for Torch programs. And the idea here is that you can take this this was released in the last release of Torch, which was in the beginning of January, I guess. And suppose you have this Torch program here that is just like a weight and a bias tensor that you multiply and add just like a linear model and compute some value here. Okay, so this is a pretty common function. It's a simple R function that is using Torch operations. And one thing that you can use, that you can do now with Torch, is that you can use this JIT trace function, and you pass the function and then an example input to that function. So for example, I'm passing a matrix full of ones of this size, and then like this becomes a function, but this is no longer an R function. This is a compiled function in something that we call Torch script. So this trfn is a Torch script function now, but it acts just like a common R function. So you can use it to compute values for and do whatever it would do before. But you can also find the graph of this function. So this function was compiled by the Torch just-in-time compiler using this trace method. And then like what it did is like it traced all Torch operations that happened when computing an example input. And it's like transforming into this intermediate representation into this graph. And why I'm saying this, why this is important. And the nice thing is that you can serialize this graph like using this JIT save function. And when you serialize it to a file, since this file is Torch script, it's no longer an R function with weights and all that. It's like something that is not aware of R at all. So when you serialize this to a file, this can be loaded into Python or into C++ without any other R dependency. So the idea is that you can write Torch code here that does some kind of transformation to a tensor and export it to any other library that can load Torch script. Okay. And today I found out that it's also possible to use the Torch serve project to serve these functions in the traced functions in like high performance environments and things like that. So you build your model in R, and then you can export it to a format that can be used by anyone without knowing about R at all. Of course, there are still some drawbacks in this approach. So for example, we still don't support NN models, so you can only trace R functions at the moment, and you can always wrap a model in a function and do what you want. So there's, in this link, you can find like a hack if you want to export an NN model, but this will be implemented in the future. Like it's not a lot of work, and we will implement probably still in Q1. And another thing that is tricky is like, if your function here has a for loop inside that depends on the dimensions of the input tensor, for example, then tracing won't work correctly, because tracing, we will record the exact operations that happened in the C++ code, and if this might be different for different tensors, then there is no way to understand this from R code, because it doesn't know at all what is R and all that. So it won't work if your function has for loops inside it. I mean, it can have for loops. It can't have for loops that depend on the tensor input dimensions. Yeah, and when we support tracing for NN models, this will also give us like speed ups for training. So this will be very nice feature that we will work in the future. Yeah, and now I'm just like some closing remarks, I guess. So how to contribute to Torch development. And I mean, no matter what are your current skills, you can contribute to Torch development. So you don't need to be a C++ expert or even R expert. If you want to contribute to Torch, and I'll give you some ideas if you want to sometime help us in the development. We have a few open issues in our GitHub repository, and if you want to like try to fix them, you can just comment there, and I'll help you as much as I can to help you figure out how to do it. If you think there's missing documentation for something, or something that you read on the documentation and it's not clear, please open an issue and say like, this is not clear in the documentation. I think it would be better this way. This helps a lot. Like Torch is a large project and it's hard to document everything like at the beginning. Like we just released a Torch in 3 or 4 months ago. So if you find something that is not clear, please open issues. We want to improve the docs as much as possible. And also open issues if you find bugs or something that you, or like if you think there is something missing that would be nice to have in Torch, you can open an issue in our GitHub repo. If you have questions about how it would be better, what's the best way to do that in Torch, you can also ask in our GitHub repo. And yeah, if you are planning to add new features to Torch, like there's a contributor to Torch, Christoph, that started implementing distributions for Torch, so you can sample from normal distribution or any other distribution with Torch. And if it's a new feature and he's implementing stuff, and if you want to like you found something that is available in PyTorch and you want to implement in R, open an issue and we can discuss, and we can like, I can help you as much as I can. And another thing that you can do to help the Torch ecosystem is to contribute extensions to Torch. So at the moment, we have a few extensions. We have Torch Vision, that is like a small extension for that is tailored for computer vision tasks. So you can like load pre-trained models, computer vision pre-trained models, and I don't know, like do some image transformations in Torch. And this is implemented in Torch Vision. There's Torch Audio by Atos, which is a colleague of mine. And he has implemented many models related to audio tasks in Torch. And it's really cool. It's a really cool project. And if you want to contribute to PyTorch, to Torch audio development, you can find the GitHub repository here. The targets package, which was like subject of the last meetup, I guess, by Will Landau, already implements serialization for Torch models. So you can use targets with Torch, and it's really nice. You can use all the features from targets with Torch with ease. We have submitted to CRAN these Torch datasets, and Torch datasets is a collection of ready-to-use datasets for Torch in the Torch dataset format. So you can easily train a model for like the dogs and cats dataset that is already there, and you don't need to implement how to download data and how to like organize the data set in folders and directories and anything like that. So you can just use this data set. We have also implemented this tabnet package, and I think this is something, this is an idea that I like, is having like packages that are like Torch is much more lower level than like anything that we usually do in R. And it's nice to have some higher level package that use Torch as a backend. So you benefit of autograd and GPU acceleration, but you pack that in an API that is more convenient for our users. Like the tabnet package implements this tabnet model in a tidy models interface. So you can use tabnet and never know that you are using Torch, but you get GPU acceleration and all that. But you just need to know the tidy models interface. And I think this is really nice. And we have also started the implementation of Lantern, and Lantern is a tidy models interface for fitting multi-layer perceptrons and linear models like logistic regression and like anything like that. And you also wouldn't need to know anything about Torch to use it. You would only use Torch as a backend here. And yeah, let me know if you have any idea or like you want to talk, and I'm happy to discuss and help with implementation or anything. And yeah, for future work, what I am thinking is like, it would be nice to have better interoperability with PyTorch. So Torch tensors in R share the same implementation as PyTorch tensors, and it's also the same as, it's the same memory model as NumPy. So in theory, it's possible to make, like, to convert torch tensors to PyTorch tensors with 0 copies, like they can point to the same address in the computer's memory. So it would be nice to be able to interop between both. So you can, like, there's an implementation of some model in Python that you don't want to translate to R. You could like pass the tensor to Python and get back the values as torch tensors with like as if it were the same language. We also want to improve performance of Torch. Currently, like Torch is fast if you have large data sets. Like it will be much faster than most of the things that you can do in R without going to C++. But there are some space through optimizations, especially in the dispatcher, which the dispatcher is like something that will take an R function and find what is the right C++ function to call. And this is quite slow at the moment. We want to support JIT tracing for NN models, and this will also improve performance, but it will also allow you to export models to like to run inference or continue training in Python or anything that you want. And also, like in the same sense of JIT, we want to have like ONNX support, so you can export torch models to the ONNX format that is highly, like at the moment, I think it's highly supported, and you can run ONNX models in iOS devices and like Android devices or Windows, like without any other dependency. So I think this is something that we want to work on in the future. And if you want to learn more about Torch, you should go to the Torch for R website that has many and updated tutorials about R. And it also has a session with many links to other like tutorials. The RStudio AI blog has many end-to-end examples about storage. So, and you should, if you want to learn more about Torch, you should definitely read the RStudio AI blog. We have the Torch book repository, which is a work in progress book about deep learning with Torch. And the package down website has guides for other specific things that you might want to do with Torch, like serialization, indexing, and we will keep adding stuff as we find missing things in the documentation. So thank you very much. Thanks very much for watching. And yeah, thanks very much, Jared, for inviting for this talk. And I'm happy to discuss anything that you want.
Thank you very much, Daniel. Everyone give a nice virtual round of applause. I see we have a lot of people typing, so let's get a few applause emojis going, and then we will start with the questions. I see a bunch of questions. Thank you. A lot of thank yous for you. A lot of thank yous. So I'll give everyone a chance to get those thank yous to you. Another question, so I'm just writing it down so people hear clicking. It's because I'm writing other questions. All right, yeah, lots of thank yous for you. So there you go. Very everyone's very busy. All right, great. If people hear that clicking, that's my computer making noises. So let me actually take that out because my microphone is right near my speakers. All right, I'm going to scroll to the list of questions I have.
Sorry, I think my connection is really slow. Let me try.
Can you hear me? Maybe not. All right, I'll give you a second.
I think my connection is really slow.
So people are saying they can hear you. Is there a lag?
Yeah, maybe it's better now.
there might be a lag, and I'll do my best to work around that lag as I ask you
guess
these
so.
questions. All right. So first up,
Okay.
There's a bunch here, so I'll try to move through quickly. Earlier in the first diagram, you talked about R to lantern to torch. So does that mean we go from R to C to C++?
Yeah, that's exactly it. I mean, you are talking here. We sorry. The question was why we need to go from R to C to C++. Is
Yeah,
that it?
why not R to C++ to C++? Why is lantern in C instead of C++?
I can't hear you.
Oh, great. How about now if I come closer to my microphone? Can you hear me? Let me see if I have a different microphone. Give me a second. Nope. Let me try a different microphone. I will try this one. Can you hear me any better now?
Sorry.
Nope. And folks, can someone say if you could hear me, if we could isolate this, if this is a issue on Daniel's end versus my end? Okay, Daniel, I'm not sure if you can see the chat. They could hear both of us. Promise, I don't think you can hear me. Am I muted?
I think it's better now.
Okay.
I changed my Wi-Fi settings, so I think it might be better now.
All right, let me know if it drops out again, and we will try to.
Okay.
I'm not sure
so sorry.
Yeah. No worries at all. So the question was, why isn't the Lantern API? Why is that not written in C++? Why is it in C?
Yeah, the main issue here is like R can only talk with things that are compiled with MinGW, which is a port of GCC to Windows. But PyTorch, because it uses CUDA and all that, can only be compiled with VS Studio, Microsoft Visual Studio compiler. And I mean, when you try to make something that is compiled with GCC to talk with Visual Studio compiler, then there are many issues because they don't use the same memory representation of objects and stuff like that. And you can, there are many segfaults all the time. And especially if you send objects that are not C compatible. So this is why we built this Lantern C API. So Torch from R can talk with libtorch compiled with a different compiler, and they can talk because it's a C API, and even different compilers are using the same memory model. So this is like, I honestly, I would never be able to do that. It was Javier Luraski that had all the knowledge to do this kind of stuff.
All right, great. So yeah, I guess the C compiler can talk to via Visual Studio compiled code better than R can. Is the
okay? This is the
And I guess they couldn't recompile libtorch from scratch for R. You wanted to go with the official compilation.
Yeah, I mean, we could compile with GCC, but then we would lose CUDA support, which was not like an option because the main point of Torch is being able to use GPUs.
Okay.
So, yeah.
Thank you. Someone asked, is it 0 or 1 indexed? I answered to them it was 1 indexed, and I assume that's correct.
Yeah, it's 1 indexed. This is something like there is a transition period, I think. Like in TensorFlow, we started with 0 indexed, and then at some point we changed it to 1 indexed, and then we came back because it was so confusing to have stuff like that. And in Torch, we decided to use 1 indexes for everything. Like if you subsets of tensors, if you do like the axis arguments of like many Torch functions have axis arguments that will like just like the apply function in R, it will apply in that axis, and everything is indexed at 1. But you might find some places that we forgot. We didn't find it was 1 indexed, But I think at the moment we probably found most of them. So, and at least you would have an error like saying this should be one indexed and do something. Please call.
It's a
Please
GitHub
open
issue.
an issue. Yeah.
Great. Yeah, except for the GPUs, those are still 0 indexed, I saw.
Yeah, the GPUs are 0 indexed, but this was by design because NVIDIA will always show stuff with 0 indexed.
Mm-hmm.
So it would be like if you do NVIDIA slash SME, you know, like to find your GPU names,
Yep.
and it would be totally incompatible with Torch, and it would be so hard to debug stuff. So this is the main point. Yeah.
That makes sense.
Yeah.
And speaking of GPUs, there's a question. A, how does this handle multiple GPUs? But B, if you do have multiple GPUs, do you have to specify when you do 2 GPU or 2 CUDA, I think it was, do you have to say which GPU you want to send it to, or can you just say 2 GPU and it will take care of it? And if you fit a model and you have 3 GPUs, does it just figure it out?
Yeah, at the moment, we don't have support for like higher level stuff for GPUs. So if you want to compute on GPU 1, you will need to move everything there and do the computation there. And if you want to split stuff into multiple GPUs, you would also need to like split your computation like that. There's no like how do I say that? Like, I mean, there's no
multi-GPU support.
Yeah, there's no multi-GPU at support at the moment, but this is not too hard to implement, and we might implement at some point of the year. Like there is an NN data parallel in Torch that can distribute computation between multiple GPUs, but we still don't support that like in a higher level at the moment.
That'd be cool. So coincidentally, I was on a call with the Rapids AI team from NVIDIA, and one of their concerns about porting it over to R is that multi-GPU support is hard. There's no built-in way to do that. So you crack that, then Rapids can come to R also.
Yeah, I mean, I don't know if this is an R constraint, I guess. Like it's just, it shouldn't be an R constraint at all. Like all this should be managed by the OS, that by like the C++ library or a C library downstairs. So I don't see why R should be blocking that. I see mostly like this compiler stuff is the hardest part for things, for GPU stuff work on R, especially on Windows. I think this is the hardest stuff.
And in light of that question, there is a question about if you have a very large data set, someone's using Spark with multiple nodes, and I think you sort of just answered it. Can Torch support distributed calculations across multiple nodes? Not GPUs, but like multiple nodes. Is that a thing?
Yeah, not at the moment. Like, I mean, you wouldn't, you could do some kind of implementation, like use your .get item to call Spark, or like in your data set, you can initialize a pool of connections to Spark, and then like do some kind of, I mean, yeah, you would need to mostly implement all this logic to pass stuff to Spark, and
you couldn't spread the computations to the other machines. You're just spreading the data.
Yeah,
pulling it into the one machine. Okay.
Yeah, I think this is mostly, at the moment you would definitely need to do some hacky stuff to distribute your model between multiple nodes and then go back and merge them some way. Like there's no high level API for that at the moment.
Does PyTorch support that on the Python side, or is that like a Torch limitation in general?
I think it definitely has some solutions for that. Like but I honestly didn't study them all. I know they have an RPC framework for doing distribution, computation distribution between multiple machines, but I'm not totally into that. Like I haven't studied that at all. So yeah.
And continuing on the same path as a question, you talked about num workers. Is I'm going to add to this question that was asked. So with num workers, is that just loaded? Is that if that was in the middle of like a neural network layer, right? Doing a neural network, does it actually do computations on both data sets loaded simultaneously? So you're computing the gradient simultaneously and everything?
No, the num workers are just for data loaders. So basically you can like you parallelize your data loading. So you are like, and this is like usually the data loading in deep learning is the bottleneck because you can't have all your data in RAM. So you need to load data batch wise, but loading data takes time. Like if you read an image from disk, this can take time. And the idea of parallel data loaders is like not having this problem of the data loading bottleneck, because you just have like 10 batches preloaded and then your model can't consume more than that in this time. So you can have like your model can be constantly using the maximum of your GPU without stopping waiting for data to be loaded. So this is the main idea.
So it's
Like,
not about doing a forward pass in parallel. It's about getting the data for one forward pass all at once.
yeah, exactly.
So the actual question was, how does num workers work with GPU? But I think you just answered that by saying it's just all about getting into the GPU. So it's not like you have to worry about the cores.
Yeah. We still like one thing that we can definitely improve in that is that like the data loader loads data in parallel, serializes the output and loads into the main R session. And we do that very naively, like it's mostly an RDS file and that is loaded to the main session. And I think Arrow, I mean, I know that Arrow supports C++, at least in the C++ library, it supports tensors.
Mhm.
So we could like, if I don't know if the R library already supports that, but it would be, we could like, instead of serializing using an RDS file, we could use Arrow to pass data between the sessions, and that would speed up a lot the parallel stuff in Torch. So, and maybe this could be used even for distribution, for like distributing across other computers also, because
That's actually exactly how Rapids AI works. They use Arrow to get it from like I guess in that case, Python memory into the GPU memory. So you do the same thing.
yeah.
And if Neil Richardson is here, he's usually at the meetups. He works at Arrow. Let us know, Neil. If you're not, I'm going to mention you on Twitter. So, and you can't just point me back to your NYR talk because you didn't talk about that there. So Neil Richardson, you're on notice to help out with this.
Yeah.
Because there actually was a question here. Somewhere I wrote it down. Where did it go? About Arrow, right? Using Arrow to load in. So I guess theoretically, I guess the question was about .get item. That you could use Arrow because you're just reading from disk, but you want to do something even better with Arrow that we need Neil for.
Yeah, I think Arrow still doesn't, for R at least. I checked it like probably a month ago and still didn't support tensors, but I think that shouldn't be also like too much work to get it, because it's already implemented in the C++ library and the protocols are all like.
I will tag him in Twitter with you as soon as this is over and be like, hey, at NPR is his name. Daniel wants you to do this. So I'm going to tag him.
Yeah.
Continuing on with data loaders, there's a question. Could you use data loaders to do a cross-validation type of thing?
I never used it for that kind of use case. I think it would be better like to usually what we do in Torch for cross validation or for splitting data is like you have in your data set, you have an argument in the initialize function that will like split data into multiple splits, and then you can like say that you want to use this split specifically, and then you just switch the data set parameter, and the data loader remain the same. You just switch the data parameter in the data set when you initialize it. So
Okay.
there are a few, if you go to Torch dataset, you can find a few examples of where we have this kind of splits.
All right, great. Along the same section of the talk, I'm trying my best to lump the questions around the same topic. What do you mean by map data sets?
Yes, like at the moment, we only support map datasets, and map datasets is like something that you can like, you have observations, and you know at the beginning, you know how many observations you will have and all that.
Mhm.
And I think it's easier when you see the other possible data sets, which are like iterable data sets. So for example, think about reinforcement learning data set. So the data set is actually like an experiment, and it's like the next observation depends on the observation that came before it.
Mhm.
And it can like it has variable length, because an reinforcement learning experiments can end as soon as like you lose it in a game, or for example something like that. So the idea is like you can have iterable data sets that you don't know how they are going to end or when, and this is the opposite of a map data set. So at the moment, we only support the common data sets that have like a finite number of observations that you already know how to load and everything. So, yeah.
Can you actually, I'm sure the answer is yes, but can you like start, if you have a model fit and you get more data, start off where the model was and then iterate? And like, I guess improve the fit, like fine tune the weights?
Yeah, in theory, like the model is completely split up of the data. So you can like train in a first training data, save that model, and then like reload it in a different day and like have more data and continue training it with new data. This works like the model is completely splitted of data. It doesn't know anything about the data set that you are
So you
using.
could start training, like you've done 20 epochs, you could start doing the 21st epoch later.
Yeah. That works just fine.
Changing paths a little bit, can you index tensors with logicals like you can in R?
Yeah, it is also supported. Like if you do like you want only the values that are higher than 0 in a tensor, you can just index x bigger than 0, and you have the index with Boolean.
This one is from me. Does Torch play nicely with the R markdown caching? Because I know Keras doesn't really play nicely with it because it's all pointers and memories. How does Torch work with that?
I haven't tried yet, so I think it doesn't work well, I would say.
Okay.
I do think it's possible to make it work well, actually, because there should be a way to like use a hook or something like that calls torch save instead of save RDS into. That's something that doesn't sound a lot of work. I can try to figure out how to fix that.
I'm going to say please do, because I did try writing hooks for Keras a while ago, and it was a disaster. So I'm hoping that your hook will work a lot, for Torch will work a lot better than whatever I did.
Yeah, I don't know. Like I never tried to do that, so I'm just it doesn't sound, but yeah, I'm not into like neater details or like are markdown details. So maybe this is very hard. I don't know.
Go knock on Yiwei's door and ask him for help.
Yeah.
Yeah, virtually.
Yeah.
All right, good. You heard it here. You promised it within 2 weeks. Everyone heard that, right? All right. Enough messing for that.
Yeah.
About Lantern. Do you need to set engine for Lantern models like you do for normal parsnip models?
Yes, actually, Lantern is like an engine for linear models in Torch, in tidy models, in Parsnip. So you can like, you initialize just like you would initialize a linear model or a logistic regression in Parsnip, and then you use set engine Lantern, and then it will use Lantern it will use Torch in the backend to feed it.
Right. So you don't even need to use, like, if you want to fit a linear model, still linear reg, use not something else.
Yeah,
Oh.
it's just a new backend for it.
And it could do, like, for linear models, you could do penalization and everything.
What? Sorry.
Penalization for a linear model. It could do regularized regression.
Yeah, it's not implemented at the moment, but yeah, you will be able to do this kind of stuff. Yeah.
Same with the Keras one. Even though Keras can do it in Parsnip, it's like if Keras don't do regularization. Same with Stan. I've had many conversations with Max about that, or many feature requests with Max.
Yeah, I think we still didn't implement that, but that it's like, yeah, it's also like Lantern is not CRAN ready yet, so it's just like an experimental project at the moment. So yeah, but I think it should be feasible to make it work like just like with regularization and all.
Great, that'd be really good.
Yeah.
There was a question, it got answered, but I'll put it out here, about object dollar method. Is that something new? But then Gavin Simpson jumped in and said it's from reference classes in R6. So
yeah,
that's been answered.
There I think one of the main criticisms for Torch is like we use these objects and it's like all new for our people. Like we are not used to R6 at all. Like it's mostly like backend stuff, I guess, like in Shiny, or I don't know, like we use it, but we don't see it.
Yeah.
But I found that it would be much easier to implement Torch using all that, because otherwise, like it would be too much different from PyTorch, and it would be hard to port models and things like that. So I honestly think that this is the right approach for Torch, but I think there's definitely space for a slightly higher level API for Torch that is still lower level, but is more idiomatic for R. I mean, like that doesn't use that doesn't show you reference classes or stuff like that. But I still don't. I'm not sure what should be that. So I'm still waiting and see like how the project matures, and then we can see what would be this slightly higher level API for Torch. I don't know. Yeah.
I'm gonna work. I don't know if the Zoom is gonna end in 2 minutes. If it does, I want to thank you now. I have more questions to ask you from people, but if it does end abruptly in 2 minutes, thank you for this talk.
Okay, thank you very much.
Yeah. Then I'll keep asking questions as long as we don't get cut off.
Okay.
Is there any benefit between the function of object versus object dollar method? Is there any benefit one over the other?
No, they are mostly the same. Like this resolves to the same C++ calculation, so okay. There's no much difference at all.
All right. Then what happens if the model, like when you fit a model, is too big to fit in GPU memory? Does it crap out? Does it write to disk? What happens?
Yeah, I mean, if you initialize your model and it doesn't fit on the GPU, you will see a out of memory error, and everything will like turn red, and you won't be able to fit it. So the model must fit on the GPU, but Torch is very, very flexible. So you could have like some models. If your model has some models, it can have like some models that live in the CPU and other models living in the GPU, and you can like just send data between them. And of course you would lose some performance, but you would be able to fit it. Another like, but usually the simpler strategy is like, I don't know, like usually your model fits in memory and it's like the forward pass that doesn't fit in memory. And like in this case, you can use smaller batch sizes, and there's you in Torch, one thing that you can do is called like virtual batch sizes. Like since the backward accumulates gradients, you can do multiple passes without calling backward, and then you call backward after some passes. And this is like virtual batch size because you pass it like 10 batches of 2, that it's the maximum that fits in memory, but it ends up that you have the gradient estimate for a batch of 20 because you did 20 passes, and then you can like virtualize your batch size. Something like that.
That's nifty. All right. I did hear somewhere that Jan LeCun was saying that if GPUs could handle, the ideal batch size is 1, but GPUs are just more efficient doing 32 or 64 or something.
Yeah. I mean, there's I think it depends a lot on the problem. Like in highly noisy data, you usually want larger data set, larger batch size, because otherwise, but
yeah, but I'm not gonna guess anything over what he says or what you say. I'll go for the two of you say.
Yeah.
All right, let's see. Then here's a question: is it likely that it could be convenient to use a non-torch function somewhere in the pipeline? And if so, how will that affect the JIT? If you're trying to use JIT over a pipeline that has a non-torch function in there.
Yeah, if there is a non-torch function, it won't be traced, and then like it won't work correctly. Like it will when you invoke the traced function, it will ignore this computation that was not using a torch function, and it will give you wrong results.
Okay.
But I think we do check like the JITed function, so you don't get these wrong results. Like when you call this, when you have these things, you will notice that you did something wrong. It won't be silent, I guess. I think we implemented that. I don't remember anymore.
And if I recall, like you have overrode things. Like if we do like X matrix multiplication Y, like the R, like percent star percent, that becomes torch MM, right?
Yeah. We have most. I think we have most of the operators in the R language implemented for Torch. So
right.
It should work. It should work. Like if you do the percent star, like it should call Torch MM and everything should work fine.
So likely, if you have a non-torch function, if it's not from a pack, if it's like base R, you'd probably be able to, like if it's arithmetic, at least you'll be able to do it in Torch.
Yeah, but I mean, if you call a base R function with a torch tensor, you will have an error anyway. Like if you have a non-torch function with a torch tensor, you will have to do some kind of like convert back to R and back to tensor at some point.
Like
so
apply won't work, or cross product won't work.
Yeah, exactly.
All right. Oh yeah. So like the training loop is written in like an R for loop. Is there any advantages to writing a C++ for loop or even a CUDA for loop?
I don't think so. Like the idea is like there's no problem in using for loops in R if the computation that you do inside the for loop is costly enough that the for loop overhead won't matter at all. Mm-hmm. And this is usually the kind of computation that we do in deep learning, right? Like the model, apply the forward method of the model is like a costly computation. Computing the backward is also costly. So the for loop overhead won't have any noticeable, shouldn't, at least for larger models, but for smaller models, it can have some noticeable overhead, but I don't think it's worth it to like implementing this as a C++ loop at all.
So then there's a similar question. You mentioned that optimizers are written in R. Do they execute on the GPU, or what's going on with those?
Yeah, I mean, the optimizers are wrappers around torch underscore functions. So if your data is on the GPU, it will run stuff on the GPU. If it's not on GPU, it will run on the CPU. But like the main computation there is like the backward, and this is all C++. Like when you use an optimizer, like the R code is just updating the weights and doing like a subtraction at some point. It's basically all it's doing, and the hard thing is backward, and this go through deep down C++.
And when you do subtract, that's still subtraction happening on the GPU.
Yeah.
Okay. We have a few questions which are in the same vein. What happens if you don't use with no grad? What happens if you don't do that? Does it?
Yeah, if you do any kind of in-place operations without disabling the auto grad, you will have an error because PyTorch doesn't allow this. I mean, it allows, but you need to. It will say that it's not a good thing. So you will see an error, and you can disable the error if you want. But yeah. You can also make a mistake and do an operation that you would want not to be tracked, and this would be a silent error, and you would see like the gradients are not okay and the model doesn't converge, and these are harder to find. But this is hard to do if you use the higher level abstractions like optimizers and NN models. It's hard to do this kind of mistake that you forget to disable the auto grad or something like that.
Okay, yeah, you don't have to do it. Then along this, there's a few gradient questions. Okay. What will it look like if you don't zero the gradient? Are you growing a list or vectors of gradients, or are you literally adding the gradients together, like summing them up?
Yeah, it literally just adds the gradient. Like I could show you, like if I do something like that, and then I get X grad, it's -5. And if I do again without zeroing it, it will be -10. Like it just adds the gradients, and that's all it does. Like,
okay. Great. This might be a syntax question. I'm not sure. Like, was there like an $X grad underscore, or is that something made up?
Yeah, I think there was something like that, right? Like this is the way you zero the gradient of X, because this is the only way to modify it, because you need to do an in-place operation because you don't have really access to this gradient. So this is the only way to zero it. Yeah.
Does JIT, so I'm not doing completely in order, I'm sort of also trying to read what people wrote. Does JIT affect model training? Like, can you JIT a model, and does that make any difference?
Yeah, in the future, like if we, when we implement JIT tracing for NN models, you will be able, like the JIT will optimize your R code, in theory, your model, and you will be able to use the JITted model to train, and it will affect mostly performance. It will be faster because the JIT can like optimize and combine some operations that are done and stuff like that.
All right. I'm hearing that my video feed might be frozen. Can you see me, Daniel?
No, I can only hear you at the moment.
All
Yeah,
right.
you are frozen.
All right, my video isn't as important as yours, so I'm gonna let you keep talking here. It looks like my Zoom sort of froze. Yep, my Zoom is frozen, so I'm gonna keep speaking.
Okay.
Okay, so someone's asking, can we get the example live code? Can like the code you actually ran in the console? Can you get that to us somewhere?
Yeah, I'll post on my Twitter like the slides and a link to the code I use it.
Great.
Sure.
Then there is a question about when your early code's in example 00, you used as.numeric. Why did you have to do as.numeric?
Oh, I think there's no like reason for that. I think I just like the way I did these examples, like I wrote the torch one and then I translated it to R, and I think I left it by mistake. Like there's no difference of doing just that. Yeah, it's exactly the same stuff.
Right. Then we have a few that are just more comments. That was pure awesomeness. The everything was great. You can't wait to try it out. Someone else says it's awesome the work you've done. They've been fitting complex geospatial models and they are excited to try this. Oh, speaking of trying this, I'm going to answer this one. Sigrid put out a blog post specifically about doing a geospatial model.
Yeah, she's working on a blog post like for predicting time series with spatial dependencies. I think it will be very nice.
Yeah, the blog post you put out already was pretty cool, so we're excited to see more.
Yeah.
All right.
Yeah, I mean, everyone that is watching, like, if you are doing something with Torch and you want to discuss and like, please let me know. And I think the best way to share is on Twitter or like GitHub issues, and please share, and I'm happy to help with code and all that. So just let me know.
I know from personal experience, I've made a few GitHub issues already, and the Torch team is very responsive.
Yeah, I try to answer as fast as possible. So.
That is appreciated. Someone's asking, is Torch available in RStudio Cloud?
Yeah, you can install Torch in RStudio Cloud. Like, there's some, I mean, it just works. There's a period that it doesn't work. It's like when I submit to CRAN, then the binaries are not ready in the RStudio package manager, and like it doesn't work when installing in RStudio Cloud because compilation takes a lot of RAM, but it should just work on RStudio Cloud. Let me know if it doesn't work. I can try to fix it.
Great. That covers just about everything. So I want to say thank you very much, Daniel. This is a fantastic talk, and thank you for doing the work on Torch, but thank you for this talk. So everyone, if we can still give another virtual round of applause, I think that's very awesome.
Thank you very much, Jared.
Absolutely. Absolutely. I saw Tommy is in here, and every so often, whenever Tommy comes to one of our talks, like, oh, damn it, I need to rewrite my dissertation again. I hope, Tommy, go rewrite your dissertation again. I hope you have a good time doing that.
Nice.
For everyone else, remember the DC videos, the ArtGov videos will be up on rstats.ai soon. This video will be up on nyhackr.org, and we'll have the February meetup announced pretty soon. We have a few months planned ahead. Looking forward to seeing all. Out. Thank you. We're going to say goodbye.
Bye. Goodbye. Thank you very much.
Thank you.
Bye.
All right. I think I'll just hang out with you as everyone trickles out. thank you everybody for coming, and we'll see you. Goodbye, everyone, and we'll kill this off.